In this video tutorial, we will look at the nomenclature of hydrocarbon derivatives such as alcohols, alkyl halides, aldehydes, amines, amides, carboxylic acids, esters, ethers, and ketones. Hydrocarbon derivatives are organic compounds that start from, or we can also say derived from, simple hydrocarbons, like this example over here. Ethane. But if we remove a hydrogen atom, like this one for instance, and then replace it with a different atom or groups of atoms like this one, we end up with a different type of organic molecule with its own unique set of physical and chemical properties. In this case, by adding an OH group, replacing the hydrogen with the OH group rather, we end up with an alcohol, with this specific example being ethanol. Now this ethanol molecule has very different properties than the original ethane hydrocarbon. While this molecule is a colorless and flammable gas, replacing this hydrogen with the OH group changes it into ethanol, which is a colorless liquid, which we typically drink, hopefully in moderation, for its alcoholic properties. As such, we call this OH group a functional group because it changes the function of the molecule. If I replace these H's with a double bond O, we get a carboxylic acid functional group attached on, with this specific example being ethanoic acid, also known as vinegar. So once again, replacing these H's in a hydrocarbon with a different atom or groupings of atoms changes their physical and chemical properties, which is why we call them functional groups, because they change or affect the function of the molecule. Now, in this course, we will be covering the following functional groups, learning what their properties are once we add these functional groups to the hydrocarbon, and how to name them properly, so the reader knows exactly which type of molecule and what kind of properties they should expect to see. When I started learning about hydrocarbon derivatives, I had a really hard time memorizing these ones over here. These ones were pretty easy to memorize, but these ones I had difficulties differentiating them because they all have a C double bond O group attached to them, which to me makes them all look the same. To help me differentiate between them, I use this little trick. How did early humans navigate at night? It's dark and it's hard to see any landmarks that would tell me which direction is north. But if you can look up and see the stars, you can see patterns in the night sky that we call constellations. To help us memorize these constellations, we connect the dots between these stars to help us draw little pictures that make it a lot more memorable. This constellation in particular is called the Big Dipper, and where the water would pour out of the Big Dipper, if we extend this line further, it always points to the North Star. And as the Earth rotates, all the other stars rotate along with it except for the North Star, which seems to stay in the one particular position in the night sky. This in turn allows us to navigate in the night without any other landmarks except for the North Star. Well, similarly, when trying to memorize these functional groups that all kind of look the same, it can be really helpful if you can come up with a mental picture, like the Big Dipper constellation, to help you differentiate between them. Let's take a look at aldehydes, for example. When I see the word aldehyde, I think of the name alderon, which sounds and looks very similar to aldehyde. But what is alderon? For those of you who are educated, Alderon is a planet from Star Wars. And in the Star Wars movie, Alderaan was blown up by the Death Star. And when I look at the aldehyde functional group, I see the Death Star shooting its laser beams at Alderaan, and then Alderaan blows up. But what is this supposed to be? How does the hydrogen fit into all this? Well, the hydrogen is a TIE fighter flying away from the explosion. I know this all sounds stupid, but it's not stupid if it works. So once again, the oxygen represents the Death Star shooting its laser beams pew 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 at Alderaan, which explodes, and then from here, the hydrogen, or in this case, the TIE fighter, is flying away from the explosion of Alderaan. So remember, the dumber your memory device, the easier it is to remember. And this memory device is stupid. So stupid it's easy to remember. Alright, so what you're going to need to do is to come up with your own stupid memory device to help you distinguish between all these other functional groups that also contain the C double bond O inside of them. Alright, let's move on ahead and discuss the grammatical rules that are used when naming each of these different functional groups. The first functional group we'll be looking at are the alcohols. Anytime you see a hydroxyl group, so an oxygen and hydrogen combined together, attached to your hydrocarbon, that molecule will exhibit alcoholic properties. Please note that the letter R represents any alkyl group, so the R is whatever the OH group is attached to. In the example of methanol, the R represents a single carbon. But if this was ethanol, the R would represent 2 carbons. And so on and so forth. Alright, so R represents whatever the OH group is attached to. Now, depending on the location of the hydroxyl group, the alcohol can be classified as being either primary, secondary, or tertiary alcohols. In a primary alcohol, the OH group is attached to a single carbon, which can only go in one direction. In a secondary alcohol, the OH group is attached to this carbon, but this carbon can move off in 2 different directions. While this, in a tertiary group, the hydroxyl group is attached to a single carbon that can move off into 3 different directions. It is important to know what type of alcohol it is, whether it's a primary, secondary, or tertiary, because as you'll see in our next video on chemical reactions, primary, secondary, and tertiary alcohols will form different products. When naming alcohols, you do have to make a suffix change in the parent chain. For alcohols, the suffix change is pretty easy to remember. They end with an OL suffix for alcohol. Well, same thing over here, heptan, ol. But because there are 2 alcohol groups attached, we have to say di-ol. So 2 of these OH groups, 2 of these alcohol groups. Other than that, all the previous nomenclature rules we learned in the last video still apply to this one as well. The longest carbon chain, where the OH groups are directly touching the carbon, is going to be your parent chain. In this case, we have 1, 2, 3, 4, 5, 6, 7 carbons. So that's why it's called heptan. But now we have to choose a counting direction that gives the alcohols, the OH groups, the lowest possible address numbers. If we count left to right, the address numbers are 4 and 5 for the alcohol group. But if we count right to left, the address numbers for the hydroxyl groups are 3 and 4. Obviously 3, 4 is better than 4, 5, so we will use the blue counting direction and not the red counting direction. Which means that our methyl group over here has an address number of 5. So 5-methyl, heptan for 7 carbons in the main parent chain, and then 3, 4 is the location of where the hydroxyl groups are sprouting out from. Di-ol, 2 of these alcohol groups are located on the parent chain. In our next example, the molecule is almost identical, but now I've placed a double bond on this side over here. What I want to know is if the double bond is more important than the hydroxyl groups. Looking at the name, we see that the double bond is located on the number 6 carbon, 6-ene. So they are still prioritizing the hydroxyl groups. The hydroxyl groups still must get the lower number. Thus, in terms of priority, the hydroxyl group outranks everything we've encountered so far, including benzene, as we're going to see in the next example. But back to this example, with everything else being the same, the hydroxyl group still located on the 3 and the 4, so 3 and the 4. Di means there's 2 of these alcohols. There's a suffix change right there. And the 5-methyl has not changed. On the number 5, there's a methyl group there. All right, let's take a look at our last example here. But first, we need to take a little detour. When alcohols are high priority and they're part of the parent chain, we change their suffix to an OL. So alkanol, methanol, ethanol, propanol, butanol. But if I were to combine 2 or more different functional groups in the same molecule, one of these functional groups will have a greater effect on the function or the properties of the molecule. And that is how chemists came up with this little priority list. So if I added a benzene, an alcohol, and let's say an ester functional group onto the same hydrocarbon, this molecule will behave more like an ester than an alcohol or aromatic compound. This is because the ester has higher priority than the alcohol or benzene groups. As such, its properties are more dominant and shine through more than the alcohol or the benzene. It's kind of like genetics. Because I have dark black hair and my wife has light blonde hair, our kids have darker hair, brown hair. Because the genotype I have coding for black dark hair is more dominant than my wife's light blonde hair. Well, it's the same thing. If I mix a carboxylic acid with an aldehyde and an amine, the carboxylic acid properties will shine through, will be more dominant. You'll still see some aldehyde and amine properties, but the carboxylic acid properties will shine through the most. To help the reader understand this, in this example, because the carboxylic acid is more dominant and its properties shine through the most, we will name the compound as though it was a carboxylic acid. However, the aldehyde will get demoted. If it had been high priority, its suffix change would have been al, so methanal, ethanal, propanal. But because it was demoted, we tell the reader by giving it its secondary name, oxo. But because it's been demoted, we now must use its secondary name, oxo. The same goes for amines. If amines are high priority, their suffix change would be amine, so methanamine, ethanamine, propanamine. But when the amine has been demoted, its secondary name is amino. Alright, so every functional group has a name change when it is king, when it is the highest priority functional group present in the hydrocarbon. However, every functional group also has a secondary name when it has been demoted and is no longer high priority. Looking back at this example, we still see 7 carbons in the main parent chain. 1, 2, 3, 4, 5, 6, 7. So that's why it's a hept for 7. There are 2 alcohol groups, which is why we use the di and then al to say that there's 2 alcohol groups attached. We are still going to count right to left in order to give the alcohol groups, which are high priority here in this case, the lowest possible number of 3 and 4. So 3 and 4. And on the number 6 carbon, there is a triple bond, which is why there's a YN there. So on the number 6 carbon is the location of our triple bond. But you'll notice instead of a methyl group in the last example, we now have a benzene coming out from carbon number 5 instead. Looking back at our priority list sheet, we've got the alcohols, we've got benzenes, and there's a triple bond in our example. So alcohols, triple bond, and the benzene. Since the alcohol is high priority, we will name it like an alcohol, but then benzene gets demoted, and we will now call it phenyl, with the YL present to show the reader that it is no longer part of the parent chain. Instead, it is a branch, so it's been demoted. Alright, so instead of saying on the number 5 there's a benzene, we instead say on the number 5 there's a phenyl group. Now, don't worry too much about the priority list for now. This will come later on in a separate video. For now, let's just focus on each individual functional group and compare them only to the benzene, alkenes, alkynes, and alkanes. The next functional group we'll be looking at is that of the alkyl halides. I believe your textbook may call them haloalkanes. Essentially, whenever we add a halogen to a hydrocarbon, you make an alkyl halide. So in this situation, X represents some kind of halogen, either fluorine, chlorine, bromine, or iodine. Please note that these guys are the lowest priority. Basically, they're considered to have the same rankings as just regular alkanes. As such, there are no suffix change. Instead, you'll just use the prefixes to identify the halogen. So fluorine becomes fluoro, chlorine is chloro, bromine is bromo, and iodine is iodo. Looking at our first example, all the previous rules we had learned still apply, so find the longest continuous carbon chain you can, in which case it is 1, 2, 3, 4, 5, 6, 7, 8 carbons in my parent chain, which is why it's called octane. No double bonds, no triple bonds, so just A and E suffix to show that it's an alkane. We then choose a counting direction, either red or blue. In both cases, the address number for my branches are 4 and 5. And 4 and 5. With both counting directions giving me the same address numbers, I need a tiebreaker. With all things being the same, let's go alphabetical order. Here we have a bromo, while over here we have an ethyl. Since B comes before E alphabetically, the bromo branch should get the lower number. So we're going to use the red counting direction. So the name is 4 bromo, 5 ethyl, and then octane. To prove that alphabetical order was used in determining which branch got priority, I copied the exact same structure on this side, but instead of a bromine, I put an iodine here. With 8 carbons, it is still octane in the parent chain, and the address numbers are still 4, 5 in both counting directions. So again, we have to rely on alphabetical order for choosing the proper direction. In this case, E for ethyl comes before I for iodo, so the ethyl branch is higher priority and must be given the lower number. Which means we are now using the blue counting direction going from bottom to top, unlike the previous example where we went from top to bottom because the bromo had priority instead. Now, what happens when we include a double bond? From our priority list, halogens are very, very low priority, and so the alkenes and alkynes are going to be more important than these ones over here. So we are still going to use the longest continuous carbon chain that we can find that includes the double bond. In this case, it is a 1, 2, 3, 4, 5, 6 carbons, which is why it's hex. And because the double bond is higher priority than everyone else over here, it should get the lowest possible number. Which means we need to count from left to right, making this 1 ene. So the double bond is located on the number 1 carbon. 3, 4 difluoro, so there's 2 of these fluorine groups on the number 3 and the number 4. And on the number 5 carbon, we have a methyl branch. The suffix change for aldehydes is also pretty easy to remember. Just change the suffix to an al for aldehydes. So instead of pentane, you would call it pentanal, butanal, propanal, methanal. With regards to priority, they are higher than alkenes, alkynes, alkanes, halides, and also benzene. You will notice that aldehydes only occur on terminal carbons where the C double bond O is located. We call them terminal carbons because that is the end of the line. The hydrocarbon cannot extend any further in this direction because hydrogen can only make 1 bond, nor can it extend in this direction because oxygen can only make 2 bonds, which is already maxed out, and so it can only move in this one direction, making this carbon an end point or a terminal carbon. Because the formal group is always at the end, and the formal group is high priority, by convention it is always going to be carbon number 1, 2, 3, 4, 5, 6, and 7 being the longest continuous carbon chain I can find that includes my formal group, and that's why the parent chain is called hept for 7 carbons inside. On the number 4 carbon there's a double bond, so that's why it says 4 ene. On the number 6 carbon we have a triple bond, that's why it's 6 in. We use the suffix al to show the reader that it's an aldehyde. Again, there's no need to tell the reader where the al is located, so you don't have to say 1-al, because by default this is always going to be carbon number 1. It's the terminal, it's the starting point. So the number 1 is not needed. On the number 2 carbon there's a fluorine, so 2-fluoro. On the number 3 carbon there's a bromine, so 3-bromo. And on the number 5 carbon there's an ethyl branch. And there we have it. 3-bromo, 5-ethyl, 2-fluorohept, 4-ene, 6-ene-al. Now you will notice there is a double bond, so we have to determine if it's in the cis or trans conformation. Let's extend the double bond with an imaginary line. And when we trace the parent chain, we do see the parent chain does cross the line from one side to the other, and thus it is a trans conformation. Very similar to aldehydes are ketones, but instead of having the C double bond O on a terminal carbon, it is now somewhere in the middle, so we're going to call it a carbonyl group. So that's what this R is for, to show the reader that the hydrocarbon can extend in this direction. And over here we see something called R prime. So this little apostrophe symbol is called prime. So we say R prime to show that it could be a different hydrocarbon going off in this direction. So R and R prime could be the same thing, in which case it's just 1 carbon, 1 carbon. Or they could be different with R having 2 carbons here in this example, and R prime having 1, 2, 3, 4 carbons in this example. The important thing is that the C double bond O carbonyl group must be in the center of the hydrocarbon and not at the end point or terminal carbon, in which case you would call it a formal group and it's an aldehyde. While if it's in the middle, it is a carbonyl group. Again, the suffix change is pretty straightforward. ketone, so your suffix changes O-N-E at the very end. So pentane turns into pentanone, methanone, propanone, butanone. And as with the other examples, the ketones are going to be higher priority than alkenes, alkynes, alkanes, halides, and benzene. Again, we're going to choose the longest continuous carbon chain that includes the ketone. So in this case, we get a 1, 2, 3, 4, 5, 6, 7. So hept for 7 carbons in my parent chain. Because the carbonyl group is high priority, it must be given the lowest possible number. So we're going to count in this direction, giving the carbonyl group, the ketone, the lowest possible number, which is a 3-one. Now in this example, you must tell the reader the location of the ketone, or the C-O. In this case, it is placed on the number 3 carbon, so that's why it's 3-one. But it could have just as easily have been placed on the number 2 carbon, in which case you would call it 2-one. Now, putting it on the number 1 carbon is not possible, so you never see a 1-one, because the moment you put it there, it's now a terminal carbon. And because the C-O is on a terminal carbon, it would now be an aldehyde and not a ketone. Alright, so 1-one is never going to happen. Moving ahead, we see 4-in to show the location of the triple bond. We see a 6-ene to show the location of the double bond. And then we have on the number 6 carbon a cyclobutyl branch, so cyclobutyl on the number 6 carbon. Now the example at the bottom is kind of a trick question. In the example up top, you had to tell the reader where the C-O is located. But for this example, a number is not necessary. If you had to put a number, it would have been a 2-one, so the location of the C-O is on the number 2. But since there's no other possible location if it's a ketone, the number 2 is not necessary. So what I mean is, placing this C-O on the number 1, it would no longer be a ketone, it'd be an aldehyde. If I try to put the C-O on the number 3, again, it'd be a terminal carbon, it would no longer be a ketone, it'd be an aldehyde. So in order for it to be a ketone, there's only one location for it to be, in the middle, and there's only 1 carbon that's in the middle. So that's why a number is not necessary. The same goes for the chlorine. Normally you would write down where the chlorine is located. So in this case, if you had to write a number, you say 1-chloropropanone, because the chlorine is popping out from carbon number 1. But the number 1 address number is the only possibility. You would never place the chlorine on number 2 because there's not enough room. Carbon can only have 4 bonds. Well, here's a double bond, here's a single. So we've already maxed out the number of bonds for the carbon atom. So the number 2 address number is not possible for this situation. So there's no need to put a number there. Now if I tried to put the chlorine on the number 3 position, we would no longer want to count right to left, but instead we would count left to right to ensure that the chlorine got the lowest possible number, which is 1. So again, since there's no other number that it could be, address numbers are not really necessary or technically necessary in this example. Alright, let's move ahead. Carboxylic acids are characterized by the presence of a carboxyl group, that is a carbon, double bond to an oxygen, and single bond to an OH. Similar to aldehydes, the carboxyl group is located on the terminal carbon. So this carbon can only go in one direction, and this carbon acts as an endpoint. The suffix change for carboxylic acids is also pretty straightforward, ending with an oic acid. So methanoic acid, ethanoic acid, pentane turning to pentanoic acid. And as with all the previous functional groups, its priority is higher than those of alkanes, alkenes, alkynes, halides, and benzene. Looking at our first example, we have to choose the longest possible continuous carbon chain that includes the carboxyl group. So that would be 1, 2, 3, 4, 5, 6, 7, 8 carbons, which is why it's called oct in the parent chain. Now, some students may ask, isn't the triple bond more important? Shouldn't the parent chain go up in this direction? Well, if you did, you'd only have 1, 2, 3, 4, 5, 6, 7 carbons in your parent chain, when 8 is a better number. So, remember the carboxylic acid is more important than doubles and triple bonds. As such, they don't have to be part of the parent chain. Instead, our priority is to give it the longest possible continuous carbon chain we can find. Because the carboxyl group is on a terminal carbon, the C-O will always be carbon number 1, similar to what we saw with aldehydes. And just like with aldehydes, there's no need for you to tell the reader that the carboxylic acid is on the number 1 carbon, so a 1-oic acid would not be necessary, because this always has to be carbon number 1. So don't label the address number of the carboxyl group. On the number 2 carbon, we have a fluoro group popping up, so that's why it's 2-fluoro. On the number 3 carbon, we have a bromine popping out, so it's 3-bromo. Now, where many students get confused is with the 5-ethynyl. So let's break this down. On the number 5 carbon, something is sprouting out. Because there are 2 carbons in this branch, we'll have an eth prefix. Because there is a triple bond present, we have a yn. And finally, because it is a branch, we have the yl suffix added on as well. Now, you may notice that there are no numbers within this branch. And since the second numbering system is not being used, brackets are not necessary in this case. As with previous examples where there's no other option, the address numbers are not necessary. So for instance, the triple bond, yn, there's no other number could be. You would never put it as number 2, it's got to be number 1 for the triple bond. Same thing with the attachment site to the parent chain, it's also got to be number 1. You would never attach it to the number 2. So that's why it's just 5-ethynyl, no need to put in the address number for the triple bond or the attachment site to the parent chain. However, there is a double bond, so let's just draw a line through it. And because the parent chain crosses this line to get to the other side, it is going to be a trans conformation. When it comes to esters, they are the weird ones. The suffix change for all the functional groups that we covered so far make sense. Alcohol, so methanol, propanol, butanol, pentanol. Aldehyde, ethanal, propanal, butanal. Ketone, propanone, butanone, pentanone. Carboxylic acid, methanoic acid, ethanoic acid, pentanoic acid. We can see where all these suffix changes come from. But with esters, their suffix change is -ate. I don't see the connection between -ate and ester. So that's just one of the issues that make esters kind of weird. The second one is esters are the only functional group where there's a space between the letters and letters. Normally you would slam them together, but in this case we are allowed to split the name into 2 halves and have a space to separate them. No other functional group has that in their nomenclature. The other thing that makes esters unique is that the parent chain does not have to be the longest possible continuous carbon chain. Instead, whoever has the carbonyl group, the C-double-bond-O, must be carbon number 1 and must be part of the parent chain, even if it is shorter. So in this example, the C-double-bond-O is located on this side of the oxygen bridge, and by definition, it must be carbon number 1 of the parent chain, number 2, and number 3. So the parent chain only has 3 carbons, which is why we have a prefix of prop. We then have an AN because it's an alkane, no double bonds, no triple bonds. And finally, we have the weird -ate suffix. So this parent chain over here is called propanoate. Now, the remaining part of the ester is on the other side of the oxygen bridge. To show the reader that it is not part of the parent chain, but instead it's a branch, we have a YL suffix. And then the bute to show that there are 4 carbons in this branch, 1, 2, 3, and 4. We then leave a space between these 2 components, so the reader knows that this is the branch, while this side is the parent chain. Let's take a look at some more complicated examples. Again, the parent chain must always contain the carbonyl group, the C-double-bond-O. So 1, 2, 3, 4, 5 carbons in the parent chain, which is why there's a pent for the prefix. By definition, the C-double-bond-O will always be carbon number 1, 2, 3, 4, and 5. Since we have a methyl group popping out from the number 3 carbon, we just say 3-methyl. On the number 4 carbon, there's a triple bond. And we end things off with the weird -ate suffix change. So the entire parent chain would be called 3-methyl-pent-4-NO8. But now we have to deal with the other side of the oxygen bridge. And I'm just going to put a dotted line across the oxygen bridge to keep the two separate from the parent chain versus the branch over here. And this little divider is represented by the gap, the space between these two names. Now the longest possible chain on this side over here that is directly attached to the oxygen bridge is 1, 2, 3, 4, 5 carbons, which is why it's called pent. But because we know it's a branch, they put an "-il" suffix at the end. On the number 2 carbon, there is a ethyl branch popping out. So here's number 2, there's the ethyl branch. And we're done. Now, please keep in mind there is no need for brackets in this situation. If you recall, brackets are used to separate or distinguish between two different numbering systems. So in this case, we've got the blue numbering system versus the red numbering system. Otherwise, how would I know if I'm talking about this number 2 or this number 2? But with esters, there's a built-in separator. This empty space separates the two sides of the oxygen bridge and helps the reader to distinguish between the branch numbering system versus the parent chain numbering system. So because of this gap, a bracket is not required. Let's look at the second example. Again, the C double bond O must be on the parent chain. So we have 1, 2, 3, 4 carbons in the parent chain, which is why it is a bute. Now, because there's no double bonds or triple bonds, they put butane to represent an alkane. And of course, we've got that weird O8 suffix. So there it is, the parent chain is butane O8. By definition, the C double bond O is always going to be carbon number 1, and we're going to count from right to left with 4 carbons. Because there are 4 carbons in the parent chain, we're going to write down butane, and no double bonds, no triple bonds, so that's why there's an AN over there. And of course, we've got that weird suffix, butanoate. So the whole parent chain is called butanoate. On the number 2 carbon, we have a bromo. On the number 3 carbon, we have a fluoro, so 3 fluoro. And also popping up from the number 3 carbon, we have the iodine, so 3 iodo. So this covers the parent chain portion of the ester. By placing a space here, we now help the reader to differentiate between the branch, so the other side of the oxygen bridge, versus the parent chain. And this also helps to separate the two numbering systems. One for the parent chain in red, and one for the branch in blue. Because the branch has 5 carbons in it, we say pent. 4-ene to show that there's a double bond on the number 4 carbon. -il to show that it's a branch. And then, of course, on the number 2 carbon, there's a chloro. All right, so with esters, please remember that there is a space between the branch and the parent chain. The parent chain must always be the one that has a C double bond O attached to it. And unlike the other examples, the parent chain does not have to be the longer carbon chain. But just like all the other examples involving terminal carbons, whoever has a C double bond O must by default be carbon number 1, which is why you don't need to write butane 108. So putting an address number for the location of the C double bond O is not necessary. It's always going to be carbon number 1. Don't need that address number. All right, and that is esters. Similar to carboxylic acids, ethers also contain an oxygen bridge. And whichever side of the oxygen bridge is longest will become the parent chain. Since the left side is longer with a 1, 2, 3, 4 carbons, the parent chain is called butane. Similar to esters, where the oxygen bridge is always on the branch, not the parent chain, the oxygen bridge is also part of the branch for ethers, which is why we call it prop. However, it is the branch that gets the suffix change, not the parent chain in this case. And so the suffix change for ethers is an oxy. So this branch is called propoxy. Prop for 3 carbons and oxy because there's an oxygen bridge attached to it. And of course we need to tell the reader that the propoxy branch is attached to the number 1 carbon, in this case of the butane. If it had been a 2 propoxy, then it would look something like this, where on the number 2 carbon we would have this propoxy branch popping out. So to summarize, for this example, we call it a butane because it's the longest continuous carbon chain. That'll be part of your parent chain over here. And then we call it a propoxy because there's 3 carbons, so prop, and then there's an oxygen bridge attached to it, propoxy, and it all sprouts out from the number 1 carbon. These next two examples are going to be a little more interesting because they include brackets, but don't let that freak you out. It's not as bad as you imagine it to be. Let's break it down, see if it makes sense. Here's my oxygen bridge. Which side is longer? Because the longer side must be your parent chain. So because this side is longer, with 4 carbons, 1, 2, 3, and 4, we will call it butane. Since we want to give this oxygen bridge, this alkoxy group, the lowest possible number, we are going to count right to left, giving it an address number of 1, 2, 3, 4. So on the number 2 carbon, I have this alkoxy group sprouting out. On this branch, we have 2 carbons, 1 and 2, which is why it's called eth. And then, of course, there's an oxygen bridge, so there's the oxy. And on the number 1 carbon, there is a chlorine popping out, so that's why it's 1-chloro. To help differentiate between this number 1 and this number 2 versus the red number 1, red number 2, which 2 are we discussing, which number 1 are we discussing, we use brackets. Everything outside the bracket is for the parent chain in red, while everything inside the bracket is for the branch in blue. Alright, so this bracketed area represents this alkoxy group branch here. In the bottom example, we're going to choose the longest continuous carbon chain again to be your parent chain. So that would be a 1, 2, 3, 4, 5, 6 carbons here, which is why we have a hex. And since we want the oxygen bridge to be the lowest possible number, we're going to count from right to left, giving it 1, 2, 3, 4, 5, and 6. So that's why there's a number 5 ine, to show that the triple bond is located on number 5 carbon. And then we have a 4-methyl. And then we have on the number 3 carbon something interesting popping up, our alkoxy branch. Once again, we need brackets to separate or at least differentiate the numbering systems. 1 for red for the parent chain and 1 for blue for the branch. In the branch we have 3 carbons, so 1, 2, 3, which is why they call it prop. And because the oxygen bridge is located on the branch, we have an oxy. Because there are 2 chlorines, each sprouting out from the number 2 carbon, we say 2,2-dichloropropoxy. Alright, so please remember that the counting direction must result in the lowest address number for the alkoxy group. So with the oxygen bridge, it won't always be a number 1. So in this case, it was a number 2 for the location of this alkoxy group. And down here, the location was number 3 for the alkoxy group. So be sure to always indicate the location. The 2 final functional groups, the amine and the amide, both contain a nitrogen atom. Because the nitrogen atom contains 5 valence electrons, you can attach up to 3 hydrocarbon groups to an amine. Just like alcohols, you can have primary amines where the nitrogen group can go in one direction, secondary amines where the nitrogen group can go in 2 separate directions, and tertiary amines where the nitrogen group can go into 3 separate directions. Again, it is always important to know whether it's a primary, secondary, or tertiary amine, because each of these can have different chemical reactions resulting in different products being formed. When naming amines, many of the same grammatical rules apply. So to find the parent chain, choose the longest carbon chain that is connected to the nitrogen atom. In this case, it would be 1, 2, 3, 4, 5 carbons, which is why it's pentan. And as before, we need to make sure that the amine gets the lowest possible number, so we're going to count from top to bottom, making this 1, 2, 3, 4, 5. As such, the amine group is attached to the number 2 carbon. Thankfully, the suffix for amines is pretty easy to remember. It's just amine. So the parent chain is named pentan-2-amine. Where things get difficult is if there are branches coming out from the nitrogen group, the amine. Remember that numbers are reserved for carbon atoms only. So how do we tell the reader that the methyl branches over here are coming out from the nitrogen and not from the carbons? Well, we use N as the address numbers instead of actual numbers. Alright, so just treat these N's as if they are just regular numbers, but instead of having these 2 methyl branches popping out from a carbon atom, they are popping out from the nitrogen atom instead. So we have N, N dimethyl pentan to amine. In our next example, the cyclopentane group over here is the longest possible continuous carbon chain that's directly connected to our nitrogen. So that's where the cyclopentanamine comes from. Again, the attachment site must always be the lowest carbon number, which in this case would be the number 1, 2, 3, 4, 5. Now, it doesn't really matter which direction I count in because it's always going to be carbon number 1 and there's no other branches that I need to worry about sprouting out from our parent chain. And again, because the attachment site for the amine has no other option except number 1, they didn't put a 1 amine numbering address system. It wasn't necessary for this situation. And like our previous example where there were 2 methyl groups popping out from the nitrogen atom, we write down NN dimethyl to show that the 2 methyl groups are popping out from the nitrogen and not from a carbon atom. Alright, so here we have N-dimethyl cyclopentanamine. Alright, so with this last example, we are again going to try and pick the longest continuous carbon chain we can find that's directly touching or attached to the nitrogen itself. So this would be the parent chain, 1, 2, 3, 4, 5, 6 carbons, which is why we have a hexane. Since the amine group must get the lowest possible number, we're going to count from top to bottom, 1, 2, 3, 4, 5, and 6. So that's why there's a 2-amine. Over here, we have a straightforward propyl group popping up for the N, so that's why we have an N-propyl. But over here, things are a little more complicated because there's a double bond, and I need to tell the reader where in this branch the double bond is located. Since this requires a secondary numbering system, brackets are required, with everything inside the bracket using the green numbering system for the branch. So because there are 5 carbons in this branch, 1, 2, 3, 4, 5, we're going to call pent. When choosing a counting direction, we need to make sure that the nitrogen gets the lowest number, but in both cases we still get a number 3. So 1, 2, and 3 going this way. Versus if we went this way, it'd be a 1, 2, 3 as well. So we need a tiebreaker. The next tiebreaker would be the double bond. Give it the lowest number. In this case, the lowest number we can give it would be a 1, which is why we have 1-ene to show the double bond location, and 3-il to show the attachment site to the parent chain, or in this case, the amine. Alright, so hopefully this makes sense. From the N, from nitrogen, a propyl branch pops out. Also from the N, a weird branch, pentyl, pops out. Why did this one go first? Alphabetical, right? P and P. But then E versus R, E goes first, so pent has higher priority than prop. And then we list the parent chain, hexane, 2-amine, location of the amine group sprouting out from the number 2 carbon. Our final functional group is the amide. Like amines, we can have primary, secondary, and tertiary amides. With a primary amide, the nitrogen is only attached to 1 other carbon. With the secondary amide, it is attached to 2 carbons. And with the tertiary amide, it is attached to 3 separate carbons. Similar to an ester, we are going to split things up. Whoever has a C-double-O will always be the parent chain, while the amine will be on the other side. So looking at our first example, we see the C-double-O is located on this side over here, so that must be your parent chain, 1, 2, and 3, which is why it's called a prop. The carbonyl group, the C over here, is going to be carbon number 1, 2, and 3. So that's why we have the 2 over here to show the location of the double bond, and then with the suffix change, it's just amide. So that makes it pretty easy to remember. Since this propyl branch is popping out from the nitrogen and not from a carbon, we can't use numbers to tell us where the propyl branch is coming from. Instead, we're going to use the letter N to tell the reader that this propyl branch sprouts out from the nitrogen. Alright, so this guy is called N-propyl prop 2-ene amide. With our final example, I'm going to cut it in half again. Whoever has a C-double-bond-O must be your parent chain. So 1, 2, 3, 4, 5 carbons in the parent chain. That's why it's called pentanamide. On the number 2 carbon is our methyl branch. So that's why it's 2-methyl. And then to tell the reader that these 2 ethyl branches are coming out from the nitrogen, we will use the address numbers of NN diethyl. So 2 of these ethyl branches sprouting up from the nitrogen each. All right, and that is our lesson on hydrocarbon derivative nomenclature.